Okay. Good morning, everyone. And I think we were here.
Morning.
I think we were here in this slide was the next slide in our presentation. This is really the last mathematician that we're going to talk about from the Greek era, and his work was in the area of areas, ultimately in the integral. This is Pappas of Alexandria, who lived much later. Look at those dates, 300 AD. This is a long way from Archimedes and Apollonius. So he's really one of the last of the great geometers of ancient Greeks, very much in Roman times. And he stated, never proved, but he stated a very interesting theorem. Historians of mathematics think he had a proof, but actually the proof does not come down to us. The proof is something which is done in Calc 2 when the integral is studied in detail. But let's just state the theorem as Pappas did, and we can show some very interesting examples of it. It's a very pretty theorem, very interesting theorem. It says if you take a plane figure, simplest one here on the left would be the rectangle, the purple rectangle, has a height of r and a length of h. So if you want to find the volume of that rectangle as you spin it around the x-axis, okay, that would clearly spin out a cylinder. What's the volume of that cylinder? The volume of the cylinder, according to Pappas, is the area of the rectangle that you're spinning around times the circumference of the center of gravity of that figure. Okay, find where the center of gravity is. Notice the importance here of this geometric object, the center of gravity, something which Archimedes showed us how to find using the method of exhaustion. Here's another classic example of the integral, finding centers of gravity. Pappas he needs the center of gravity so that he can apply his theorem. Find the center of gravity. Find how far away it is from the axis, x-axis, and find that circumference. What would be the circle that center of gravity, that point, would spin around? Multiply the area of the purple rectangle times that circumference of the motion of the center of gravity, and that's the volume. Very interesting theorem. Let's see how it works. We know what the volume of a cylinder is. The volume of a cylinder is the base times the height. Well, notice that the base is a radius of r, and so therefore the base of that cylinder is going to be pi r squared, and the height of the cylinder is h. So we know from other considerations that the volume of that cylinder is pi r squared h. Let's look at Pappas's theorem. Now it's easy to know where the center of gravity of the cylinder is. It's a completely symmetric object. It's right in the middle. It's in the middle of the length and it's in the middle of the height. It's dead center in the middle. And so therefore the distance that the center of gravity is from the x-axis would be half of r. And so the circle that point spins around would be pi times r over 2 squared, pi r squared. I'm sorry, pi r over 2, the circumference, not the area. It's the circumference, the length around that point spins as the whole figure goes around the x-axis. So if you look at Pappas's formula, the formula for the volume, he says, is the area of the rectangle, which is r times h, times the circumference of that point as it goes around the x-axis. Well, the circumference is 2 pi times the radius of the circle, and the radius there is r over 2. So if you multiply all that up, RH times 2 pi times r over 2, sure enough, you get our volume formula, pi r squared h. Very interesting formula. Let's take a look at the second one in the middle. Let's take a triangle and spin that around the x-axis. Then we're going to get a cone, and we're going to get the volume of a cone. Again, we know the volume of a cone. Volume of the cone is very nicely related to the volume of the cylinder. It's exactly 1/3 of it. You take that pi r squared h and take 1/3 of it, that's the volume of a cone. Let's see how Pappas's formula works out to reproduce this formula. We need to find the center of gravity. Remember, we know how to do that. We take the medians, that is from the vertex to the middle of the opposite side. Those are called the medians of the triangle. They intersect at one point at the centroid, at the center of gravity. Okay, so there it is. There's the center of gravity there, C. But how do we, we need to know what the circumference of the circle is as we spin that point around. Well, if you remember again, we took from Euclid the theorem that center of gravity, that centroid, has a certain relationship between the vertex and out to the opposite side, to the middle point. That always divides that line, the median line, in the ratio of 2 to 1. And actually, Archimedes used that, if you recall, in his work. So we can therefore write C in the. Could you please mute yourself? Everyone should mute themselves except Mike. I appreciate it, so there's no background noise to the class. Everyone should mute themselves. Thank you. So if you can see that we can write C as a in a proportion. Notice that this triangle here is certainly proportional to this bigger triangle here. They're two right triangles where these two lines are parallel. So you can see that that this length here, that this height C is to 2, as this height here, R over 2, is to 3. Okay, so that's a little proportion. Okay. C is to 2 as R over 2 is to 3, because this right triangle here is similar to this right triangle here. Well, we just need to cross multiply and find that C is R over 3. Okay, so that's the distance that the centroid is from the x-axis. Now, applying Pappas's formula, the area of the triangle, of course, is 1/2 the base times the height. 1/2, here's the height, R, times the base, H, times the circumference, which is 2 pi R over 3. And if you multiply all that up, you will get 1/3 pi R squared H. Here's a clever use of it. Let's take the semicircle and spin the semicircle around and get a full sphere. Now, we know Archimedes, of course, tells us what the volume of the sphere is, 4/3 pi R cubed. We spent a lot of time going through Archimedes' beautiful proof of that result. Not so easy to find the center of gravity of the semicircle. That's not an easy problem. That's something which we would do in Calc 2 using integration. But we can work Pappas's theorem backwards, since we know what the volume is. And if we just call this distance C, whatever it is, the distance from the x-axis up to the center of gravity of the semicircle, and then Pappas says, well, take my formula, take the area of what we're spinning around, which is 1/2 the circle, 1/2 pi R squared, times the circumference that the centroid would go around, 2 pi times C, whatever that radius is. That simplifies to pi squared R squared C. Pappas says, according to my theorem, that's equal to Archimedes' volume, 4/3 pi R cubed. And from here, right, using algebra, right, we can solve for any unknown we like in the equation. We can solve this equation for C. A couple of steps will take us to C. Not an obvious answer at all, okay? That the distance from for a semicircle from the center is 4R over 3 pi. It's a strange and very unintuitive number, but Pappas's theorem actually gives us that, because we can back into it by already knowing the volume of the sphere. So just a kind of the last hurrah that the ancient Greeks had in terms of the problems that will eventually lead to the calculus, the problems of finding the construction of tangent lines and finding volumes. And here, Pappas has a very neat way of finding volumes of revolution. Remember, Archimedes showed how to do this in general. Archimedes could take any kind of a figure, for example, the paraboloids, the segments of parabolas, and all kinds of other geometric objects. He could do it using the method of exhaustion. What Pappas is doing here is, as if you have a simple figure, right, in which you can know what the area is, and you can find what the centroid is, which is not easy every time. But if you could find those two things, then this is a very neat formula to show how the volume around the x-axis will spin out. Okay, so we're pretty much finished with our discussion of Greek geometry and its relationship to the history of the calculus. So the limitations of the Greeks, why, for example, did the Greeks not go all the way and be able to actually invent the calculus as we know it? Well, they had some very severe limitations. One particular is that they always emphasized geometry over algebra. That geometry was much more important to them, and they developed geometry much more than they developed the algebra. For example, in their work, they always thought of their numbers and their figures in terms of lengths and areas and volumes, not just as abstract numbers. For example, you couldn't multiply the length of a line times the area of a square. You couldn't do that. That didn't make any sense unless that line was developed into a length, to make the solid of the volume. But just to take an arbitrary length and an arbitrary square and multiply those two numbers together would make no sense to the Greeks, because that was not any kind of a geometric figure being formed. Things like this, things which we would do naturally without thinking, they would not do, because their logic was so precise and their numbers only represented geometric objects, and therefore they had to stay in those geometric rules. They did not give themselves the permission to be kind of like a Wild West and just multiply these numbers abstractly. And this very much held them back. The procedures that we saw, I think everything that we've seen here from Euclid and Archimedes and Apollonius, all of these, the geometry that I've showed you, I think you'll agree, none of those things really lead to an algorithm. They're all one of kinds. They're all these brilliant insights, these things to do for that particular figure. You need to have some kind of a real insight, to that particular problem to crack it. That's the exact opposite of having an algorithm. An algorithm is this mindless thing where you just have a crank to solve. You crank use the same crank with just different numbers. That's not the character of Greek geometry, and therefore you're not going to be able to develop a lot of powerful methods if you're always relying upon these genius kind of ideas to solve these problems one at a time. They certainly also were very severely hampered by their number system. Their number system was, even worse. It was worse in a sense than the Roman numerals. So to do algorithmic computations of difficult multiplications and divisions and taking square roots was very, very difficult to do. They did not have certainly any algorithms to do that. The kind of work, for example, that Archimedes had to do to find those, those inscribed and circumscribed polygons of sides getting bigger and bigger and bigger. The computations that he had to do were very, very complex, whereas even if we just had the decimal system, they would have been much, much easier to do. So these are the general, some of the general ideas that were hampered the Greeks. As brilliant as they were, as beautiful and as powerful as their geometry was, they really were hitting some kind of a barrier because of these ideas. Being too cute by half, what I can say is what they lacked was the Arabic numeral systems and ninth grade algebra. And that is a silly thing to say on one level, but there actually is some truth in it on another. This is, if you want to summarize what they didn't have, that if they could have had, what people had later on that they didn't have, what made a great difference to have the breakthroughs to bring modern mathematics, you could summarize it by that. Very, very quickly, we just want to mention, I did suggest a couple of videos to watch about the history between the Greeks and the Renaissance. But the two big contributions that we just want to mention is the introduction of the Arabic numerals. They're called the Arabic numerals, but they're actually invented by the Indian mathematicians 500-600 years before that the Arabic astronomers incorporated in. They clearly saw the superior nature of the decimal system and the place value system. Interesting, this famous quote by Laplace, one of the great mathematicians of his era, kind of puts very well to read that, how we take it for granted now, but what a really brilliant idea this place value is, to create algorithms that we can do our add, subtract, multiply, divide, and take roots. Interesting about how these numbers, the figures themselves, the numerals, how they finally settled down to be standard. They were kind of all over the map when you look at the Indian version compared to the Arabic version, compared to the very, very early, late Middle Ages version. They kind of were similar, but they really were all over the place. It was when the printing press was developed, when printing was developed, Gutenberg and those people and the printers wanted to have a standard set. They wanted to have a standard set of letters, and they wanted to have a standard set of numerals. And that's actually when the 10 numerals were finally standardized by the process of printing. And there's, of course, the famous addition to the decimal system, having 0 as a new place value. The Islamic mathematicians, just to mention them for a moment, the mathematicians of the Islamic era, very much like the mathematicians of the Indian era of about 500 years before, they were primarily astronomers. They were not mathematicians the way the Greek mathematicians were, who were just geometers. The people who did math in both those societies were actually astronomers. And so their interest was in things like trigonometry and spherical trigonometry. So why calculations were very important to them. In the Greek world, calculations were not, that was kind of done by people in commerce. That was below the geometers. Whereas the astronomers were very much interested in calculations and were disposed to look for a much better system. But what the Islamic astronomers and mathematicians did, they were able to not only preserve the works of the ancient Greeks, they were able to translate them into Arabic. Not only were they able to absorb them and understand them, but they were able to extend them in important ways. But interestingly enough, as they extended them and generalized these results of Euclid and Archimedes and Apollonius and all the rest, they never actually broke out of that paradigm of Euclidean geometry. Those limitations that I mentioned in the previous slide, they were basically working under those as well. They did not able to make that breakthrough that we find, that I'll come to in a moment, in the Renaissance.
Peter?
Yes?
This is Carl here. Could we give a shout out here to the Mayans, who also at this time worked with place value and developed the concept of 0 independently?
Very good. A shout out to them. Having no influence on our story, but an absolutely shout out to them. The interesting thing that the Arabs were able to do in terms of algebra, they began to move away from the purely rhetorical algebra. It's almost impossible for us to imagine doing algebra purely in words. The Indians did it in poetry. I mean, it is compared to us throwing around, adding x's to both sides and and cross. They had nothing like this. They were working in words. And we find it with the Islamic mathematicians, they began to start to use abbreviations for certain concepts and quantities that began to reoccur. They began to use abbreviations for some of those things, getting rid of the full words, and their algorithms could begin to appear, could begin to be realized. Once you began to have some kind of abbreviation of just the notation that you're using. So this is where it starts. It starts that movement, that essential movement in algebra starts again with the Islamic mathematicians. I just want to mention one particular person of the Islamic period. His Latin name comes down to us as Al-Hussein. He was an astronomer primarily, as almost all of the Islamic scientists were. Their primary focus, besides medicine and things like that, if you were in pure science, you were an astronomer. Therefore, they were very interested in optics. Not that they had lenses or anything like that, but taking measurements in the sky, understanding how the sky refracted light. And when you were seeing a star kind of close to the horizon, you realized you were not seeing it in its true position because of the law of refraction, because the thick air was bending the light. They studied all that very, very carefully. So their interest in astronomy also gave them a tremendous interest in the physics of optics. And here's a picture from later, translating his work into the late Middle Ages, and you can see the optical kind of images in the front plate. Here's a rainbow, and here's the sun coming down to these mirrors, and the mirrors were burning the ship, very, very much reminiscent of Archimedes' mirrors, because Alhazen studied mirrors and the focusing of mirrors. Here's an interesting idea of perspective, showing perspective, which began very, very primitively began. And this time, of course, most Islamic art was not done with this kind of work. It was very abstract geometric figures, but you can see the clear approach or attempt at perspective, where here the ramp is getting smaller and smaller, and these figures here are much smaller than these figures here. Here's someone looking through a lens or a mirror. Here's some kind of an image, this kind of thing. I just wanted to show you one example of how the Islamic mathematicians generalized the work of the Greeks. And this is kind of a neat one. You remember our friend Hippocrates, who was trying to find the area of lunes, the first thing beyond a circle that people's trying to find the area of. And so he picked those circular-like figures being created from two circles. Let me stop talking and find this thing for a minute, guys. Here we are. If you remember the wonderful theorem of Hippocrates on the lunes, if you just look at this one half of the picture, you may recognize this. Here's our lune, and he's able to find that the area of this lune is the same as the area of this triangle. His theorem is very nice. He shows that this semicircle here is exactly half of this big semicircle here. And so therefore the quarter circle of the big semicircle is exactly the same as the smaller semicircle. So this semicircle has the same area as this quarter circle. Well, look, the semicircle is the lune plus this figure, and the quarter circle is the triangle plus the same figure. And so therefore the lune has the same area as the triangle. And this is the first time in history. By the way, this is the oldest theorem that comes down to us, written many, many hundreds of years later by one of the Roman Greek commentators. But he reproduces Hippocrates' proof, which I showed you. And Alhazen makes a very, very nice generalization of this. This half picture here is Hippocrates' picture that comes down to us. So look at what Alhazen does. He says, well, that's just a very special case of this kind of a figure where the changing lunes on both sides, the changing lunes are always equal to their equivalent triangles. A very, very nice generalization of Hippocrates' theorem. Okay, and this is just a taste of the kind of extensions, the kind of brilliant extensions, the clearly absorbing and completely understanding the work of the Greeks and be able to extend them in every way. And they were able to do that, most importantly, in making refinements to Ptolemy's system of the Almagest for the Earth-centered solar system. So that's about all that we can say, all the time that we have for that. And I'll just mention, just very briefly, leading up to the Renaissance, the person who's given credit responsible for bringing these changes to Europe is a man by the name of Leonardo of Pisa, better known as Fibonacci, who lived, you can see, a long time ago, 1200. And his father was a merchant who traveled widely through the Islamic world, even as far as the Indian world, and brought back this mathematics. And his son was with him, and a very talented mathematician himself, and really introduced these ideas to the Europeans. And interestingly enough, the first people to take this up were the merchants. the merchants saw right away that this was a much better way to keep their books and to calculate what they had to calculate than the theoretical astronomers and mathematicians of the late Middle Ages. It was the merchants who took this up and really began to spread it, and that's how it developed. Another figure I want to mention, because analytic geometry plays such an important role in our story, that Nicholas Orin, a bishop, actually gives the first kind of a graph that we have. And you can see his work. You can kind of recognize kind of the bar graphs. And here's an example. In studying, for example, a uniformly heated bar, he would describe it in this way. He would kind of have the bar out, and the heights of his bar graph would give the temperature. So here's an example. Here's how he would write a temperature, a bar that all had the same temperature. More interesting for us here is how he shows, and you can see the pictures here on the right, this is how he would show a uniformly increasing speed with these changing, getting higher and higher bars. He did not develop this into an elaborate algebra that, of course, had to wait, 200 more years. But this basic idea, starting with what we would now call a bar graph, is a short step to having, the graphs that we are more familiar with, the actual curves of analytic geometry. So we certainly want to give, talking about shout outs, we want to give a shout out to some of these great pioneers who had a great influence. According to the historians of mathematics, his work had a great influence on people like Galileo and Descartes. And of course, once it gets into their works, it becomes what all the mathematicians after them are studying. Just to remind you of the 100 years before our era, from 1450 to 1550. Yeah, talk about living in interesting times. So you can look at that. These are all events that you are very well aware of. Just wanted to kind of show you that, to show that, yeah, we have coming into a different kind of a world, a world that we can more recognize. And the great genius of the time, Leonardo, you can see his studies of the projectile motion finalized in the work of Galileo, which unfortunately we will not have time to do. We did do it in the algebra class in the fall. And here's his study of circles. And sure enough, here are the lunes of Hippocrates and Alhazen. Lunes here, there are lunes here. Here he is working on the problem of trying to square the circle, trying to find a solid figure, rectangular figure, some sort of figure of straight sides that would have the same area as the circle. And here, as an artist, as an engineer, as a mathematician, he's trying to solve the problem, geometrically, but as an artist, almost trying to visualize how this thing would go. So this is a page from one of his many famous notebooks. And finally, one last mention, the last thing we can do is just mention this is finally the development of 9th grade algebra. And it begins really with this man here, this French mathematician, Francois Witt. And he finally moves away from the words, from writing out sentences, and begins to use abbreviations, begins to use what we would call algebraic symbols. He starts in a very interesting way. For his knowns, he uses the vowels, and for the unknowns, he uses the consonants. So he has a very nice dichotomy. So when you see his equations, you can right away recognize what are his unknowns, what are the variables in his equations, and what are the constant numbers, which are unknown but kept fixed. So all of a sudden, we can start to see the visual power of using this kind of algebra.
Peter, may I ask a question?
Question?
Yes, may I ask a question? So, I mean, I'm very ignorant about mathematics, but does that continue to this day with knowns and unknowns?
No, I was just about to say, thank you. You anticipated my next sentence. Interestingly, Fermat, who was taught by the teachers, by the students of Witt, he continued to use this kind of a breakdown. Descartes was much more interesting. Descartes is the one who begins to use the letter, letters from the beginning of the alphabet as the knowns, and at the end of the alphabet, X, Y's, and Z's as the unknowns. And that turns out to be what stuck. It's a much more useful than having these things spread out between the vowels and the consonants. This is a much more reasonable way, and this is what stuck. One of the reasons historians of mathematics say that Fermat's work did not catch on as powerfully and as quickly as Descartes is because he continued to use the symbolism of Vite, which was really falling out of favor, and everyone was following Descartes' notation, and therefore people were paying more attention in the beginning to the work of Descartes. But I just wanted to mention here is the beginning of what we would call ninth grade algebra. And historians will tell you Descartes' work, as complicated as it is, we couldn't be able to follow his actual mathematics. He's working at very, very complex problems, but we could understand his notation. If you saw the geometry and you saw his equations, you would at least recognize them as, algebra equations. You would know what X and Y, you would realize, he, for example, stopped using AA and began using A squared. So Descartes introduced quite a bit of modern notation into mathematics, whereas Fermat did not. So, okay, well, that's it, guys. Let me stop for some questions. Is there anything in the chat box, Mike, or is any, let's get to that and then open the mic for other questions.
The only thing in the chat box was before the class. Antonio was wondering what kind of paper they had back in the 1500s and 1600s. Was that an economic barrier to some of this?
Paper finally wasn't brought in. The parchment was used, and stuff. Paper was not really needed until the printing press, where a tremendous amount of books finally, comparatively, tremendous amount of books, and that's when paper was beginning to really develop. The whole history of paper is a fascinating one. I recommend you Google that question, and you will be reading fascinating stuff about the history and the development of paper. Any mathematical questions about what we've done so far before we enter into the derivative?
Peter, I was wondering, when you were talking about the Greeks focusing on the problems of volumes and shapes, and that limiting their approach to mathematics, what sort of problems that we now see commonly used in mathematics were foreign to them? For example, maybe the average height of a room of people, would that be something they would think of as a numbers problem?
Oh, yes. No, I mean, you can go back and there was algebra problems done, kind of puzzle problems given to students of that kind of flavor, kind of the famous algebra problems, age problems and things like that. You'll find those in the Greeks, though they solved them rhetorically using words. What I was thinking more, Mike, was the geometric problems. For example, the Greeks had very few curves to work with. They had the straight line and the circle, right? That's Euclid. They had the conics, okay, 3 families, ellipses, parabolas, and hyperbolas. And they had literally a handful of other curves, like the spiral of Archimedes, like the tractrix, like the cissioid. They had very, very few. Whereas once we come to analytic geometry, I can just make up one. X squared plus 5x is equal to y cubed. Well, that's a curve. That has a locus.
You're breaking up.
And you
now,
could go ahead and study that locus. And you could ask all kinds of questions about it. You can ask how long the line is, from one point to another. You can ask, the volume underneath it and the tangent line, et cetera, et cetera. So the algebra opened up, analytic geometry opened up a whole world of problems that the Greeks really didn't see, weren't concerned with. So that's more what I was thinking of. Does that answer your question in some way, Mike?
Yes, I think so. I mean, the difference between focusing on conic shapes versus the Arabic community focusing on astronomy. That seems to me to be a very crisp example of what would lead you in different directions. Of
But no, I want to let me clarify that the Arabic astronomers completely mastered the work of Apollonius, knew everything there was to know about the conics, translated his work and extended it, extended his theorems on the conics. No, they were able to absorb all of Greek mathematics and extended. And it turns out that the conics, can be useful in the world of optics. How Hussein was interested in spherical mirrors. I don't know if he actually studied elliptical mirrors, but here's a problem that Hussein tried to solve, but he couldn't. Remember the problem of Heron, in which he solved the problem with a straight mirror. If you had a laser pointer and you pointed a mirror, a beam down to a place on the mirror, where would it bounce off to? Where would you have to put your eye to see it? And that's the law of refraction. Al-Hussein tried to solve the same problem for a spherical mirror. That is, if you take a laser pointer and shine it on a spherical mirror at an arbitrary place on the spherical mirror, where would that laser pointer wind up? And he tried to solve that for different kinds of shapes. And he was not able to solve it in the general case. But these are the kind of problems that they tackled, very much geometric problems which involved optics. So I hope that clarifies that a little bit better. All right, well, with the time we have left, let's see how far we get with this. You can see I've picked a whole bunch of examples of finding tangent lines. We're going to talk about the derivative. And each one of these, how Descartes did it, and Fermat did it, and Robomow and Barrow. We'll take a look at these examples as we get closer and closer to what's in the middle. And I hope you recognize what is in the middle. That is the derivative, okay? This is the change in y over the change in x, okay? If x goes from t to t plus h, then its change is h. So here's the change in y because y is equal to f of x. So here's a y value and here's the y value. So here is the change in y and the change in x. And we want to see what that change happens as the change in x gets smaller and smaller. This is the definition of the derivative. And if you remember, if you had a chance to look at the videos of last week on the derivative, those videos began to show you some of the algorithms, how to take x squared and x cubed and just turn them into the derivative, not having to go back to this formula over and over again, taking limits, but to develop almost a table of a medicine box, of derivatives, just by looking up tables, doing this once and having them available to you. But this is the definition. This is how you define this. So let's start with the two people who began this all, which is the beginning of analytic geometry. There can be no calculus without analytic geometry. It's really as simple as that. There cannot be the modern ideas of the rate of change, the modern approach to finding areas in these powerful algorithmic ways. So you don't have to be Archimedes to find volumes. You can only do this by the methods of analytic geometry. So I think the videos that we've had some background on Fermat. But one thing I want to mention is, how did he get into analytic geometry? How did he invent his version of the analytic geometry? Well, very interesting. One of his very early works is called On the Method of Determining Maxima and Minima and Tangents to Curves. He was studying that problem and, came across his methods of drawing tangents and finding max mins and therefore finding slopes of tangent lines, okay? So he began actually with algebraic problems. He began from the teachers of Wied. He began with equations, and he wanted to find, when the equations in x and y for what value of x gave the highest value of y, for what value of x gave the smallest value of y. He began with algebraic equations and moved into trying to make them into a geometric configuration. This is how he developed his analytic geometry. Sweats is a simpler approach. It begins with the algebra and he geometrizes the algebra. And you can see very much just with the title of his work. And you can recognize there on the left the drawing of the tangent line. Oh, I'm sorry. And the other thing I wanted to mention is where he begins that problem is he wants to take one of the lost works of Apollonius, okay, plain loci, which is something that comes down to us. Some commentator after Apollonius tells us about this work of Apollonius, describes some of the theorems that Apollonius proves, no proofs, just kind of a high-level description of this work, and it's lost. This became very fashionable in the late Renaissance for mathematicians to try to restore from the comments that were dribbled out from later writers to try to restore the works of the great Greek geometrists. And Fermat tackled plain loci. He was going to rewrite plain loci that he thought would have been produced by Apollonius. And this was a little cottage industry by all the great mathematicians. This is where you have people like Galileo reading Archimedes' work and reading about different volumes of different kinds of shapes and volumes. He would go ahead and take another volume and go ahead and do that. So, and this turns out to be where analytic geometry gets its beginning from Fermat in his endeavor to restore a lost work of Apollonius. So you can see, guys, the continuity here is quite incredible. The work of the Greeks is right there for them. This is where they start. Descartes, of course, is a totally different animal altogether. He was a brilliant mathematician, no doubt, but only really one major work comes down is the geometry, that appendix, the discourse on method. And he begins from the opposite. He begins with a very complex geometric problem. From Apollonius, by the way, I don't even want to describe it as a problem that involves the loci of 4 lines and angles from that the 4 lines make in the locus of 2. He takes this geometric problem and begins to work it algebraically. He starts from the geometry and develops the algebra to try to turn his geometric problem into an algebraic problem by beginning to draw axes and drawing equations which would describe the curves and stuff like that. He starts from the opposite side. But ultimately, they both, develop the concepts of analytic geometry. Just to show an example of turning, a locus into an equation, we'll take a simple one. Let's take the circle. The locus of a circle, right, at a center O and radius R, is a set of all points equidistant from O, a distance R. So there's our locus. And if you take an arbitrary point, then that point would be on the locus because it has a distance of R from O. Now, if you take another point, so let's say our radius is 5, we'll take an example. Here's a point, 3, 4. 3, 4 is on the locus because its distance from the origin is indeed 5. We can see that from the Pythagorean theorem. 3 squared plus 4 squared is indeed equal to 5 squared. So the point 3, 4 is indeed on that circle. It fits the locus. Okay? Okay. And so therefore we could say that the distance from 0 to from the O to A is, in fact, does fit that locus equation. We take our general point here, call it Z, has its coordinates x, y. Well, according to analytic geometry, that means it has an x, it has a x coordinate out here of x and a y coordinate here of y. That's why it's called xy. It goes out on the x-axis, this distance x, and it goes down this distance y. And if this point is on the circle, then it must be the case that x squared plus y squared better equal 5 squared. That's the only way to get on that circle, is to make that Pythagorean equation true. And there's the equation of a circle. Okay? There's the equation of a circle of radius 5. x squared plus y squared is equal to 5 squared, equal to 25. So a simple example of turning a geometric locus into an equation. X squared plus y squared is equal to 25. The general equation for a circle centered at the origin of a radius r would be x squared plus y squared equal to r squared. So here now we can write down the equation of any circle who has its center at the origin of any radius we like. We can generate circles to our heart's content. You can see the power of this method, as opposed to how much hampered the Greeks are by drawing one circle at a time, kind of in the middle of nowhere. The circle is, floating in the middle of space. Okay, so let's start. Let's take a look at how these geometers of the late Renaissance of the 17th century began to develop, finding tangents. Remember, these are geometers first. Okay, we'll take Descartes. But his primary thing is to try to construct. He wants to construct the tangent line. We're not quite there yet. That all we have to do is find the slope of the tangent line. That's going to come a little bit later. Descartes is still a geometer, and he wants a tangent line. Well, he's got to find the tangent line. He's going to use algebra to do it. True, he's going to use his analytic geometry, but his focus is to find the line. Okay, so here's this very clever idea. We'll take our favorite curve, a parabola, y is equal to x squared, which, by the way, he takes as his first example to demonstrate the example, so we're not cheating. And we'll take an arbitrary point, x1, and of course that point on the curve is x1 comma x1 squared. That's the locus. Y is equal to x squared. So here's our point P. He wants to find the tangent line at P. Here's his idea. He says, suppose we could find a circle that has its center on the axis, find a point 0C. Clearly it has the x value 0, it's on the y-axis, and it's up a certain height C. If we could find a circle that just touches the parabola at that one point, if we could find a circle that was tangent to the parabola, then wouldn't the tangent line to the circle also be a tangent line to the parabola? Very clever idea. If the circle only touches the parabola at one point, and the tangent line to the circle only touches the circle at that one point, then it has to touch only the parabola at that one point. And so that would be a way to find the tangent line to the parabola by finding that circle and finding the circle that just touches the tangent line at that one point. Now, let me stop you before you say, oh, but Peter, there's a point on the other side, right? Actually, the circle touches it on two sides. Guys, Descartes and Fermat did not recognize negative numbers. They only worked in the first quadrant, okay? We aren't there yet with negative numbers. Negative numbers to them were a mystery. They were, some kind of weirdness. So they were only concerned with figures in the first quadrant for solutions like this kind of a thing. Okay, so let me show you. Let's give an animation of what he's looking for. The moving picture, of course, always is always better, right? Mathematica has to get all the gerbils out here. Okay, here we go. Thank you, Mathematica. Let's take a look at what Descartes is looking for. So he's got his parabola, and he's looking for this point that will just have the circle touch the parabola, to be, in a sense, tangent to the parabola. He's got to find that good C. Oops, I'm sorry, wrong one. This is the second. I'm showing you my second animation. I'm showing you his solution. Let me show you the question. I think here's the question. Oh, yes, here's the question. Okay. He's got to find the point C that when he draws the circle from C, of course, it's got to go through the point, right? We know wherever point C he picks, he wants the circle to go through the point. He wants the circle to go through it only at that point. He doesn't want it touching at another point here. This circle is too big, right? So he's got to move up and down. He's got to try to find the good C just that point that will just touch the circle at the one point. Okay, right there. Okay, this is, all these circles are too big, they're no good. How does he find just the good point? Well, he's going to find it using algebra. Okay, that's the great leap forward. Okay, here where we're going to take a geometric problem and solve it algebraically, and we have the marriage of algebra and and geometry. Okay, so everybody see the problem? You can pick any C you like, okay, and the circle has to go through this point because we're trying to find the tangent line at this blue point. We just want to find the circle that only touches the parabola at that one point. Okay, so he uses algebra to do that. We're not going to do the details of the algebra, but let me just give you a hint of what's going on. So he wants to find this tangent to the curve. Well, here's the equation of the circle. Take my word for this. Notice it is very close to our circle equation that we derived. Notice that's because the center is up here at C, it's not just y squared, but it's y minus c squared. So some of you may recognize that as the equation of the circle off of the center, off of the origin. If you don't, take my word for it. That's the equation of the circle at center 0, C. He also, of course, has the parabola, y is equal to x squared. He wants to find where these two curves cross, but they only cross at one place. If r is too big, it'll cross at more than one place. If r is too small, it won't reach the parabola at all, and it won't cross at all. My goodness, what you'll get there is an imaginary number. They didn't want to deal with that at all. Okay, if you picked r too small, you would get c to be, you know, a number with the square root of a negative number. Oh my goodness. So they were trying to find the solution to these two equations that would just give one solution, and that would be the tangent point. So just to extend the algebra a little bit, here, if this is the point x1, then this is the length x1. And so we have a formula, right? Because if this is c, this is the good number we're looking for, and here's the height x1 squared. So this, right, this is the height x1 squared up from the origin. And here's c minus x1 squared, and here's x1. So these two guys have to fit the Pythagorean formula, right? So I can write that down. R squared is equal to the x1 squared plus the c minus x1 squared. So he has a series of formulas he can work with. Here's take the original formula for the circle, take the whole circle itself, but don't write x squared, write what x squared is equal to, y. Okay, so we have another formula here. So he can work these formulas using his algebra. And notice what he has here. He has a equation with just two unknowns, y and c. x1 is presumably known. This is a known point he's working with. So he has an equation in y and c. He wants to find a solution for c that only gives him one y. Okay, that's what he's looking for. And algebraically, he can do that. We don't have time to do the algebra. We need to go into the quadratic formula and all that kind of good stuff. But the point is, he is able to do this and in the process, you know, develop analytic geometry. And so here is his solution. Now, as x changes, he's always finding the good c right away. The good c is being yielded to him by the algebra, and he's immediately finding the good circle. And of course, then given any circle, Euclid shows him how to draw the tangent line. Notice this is very clever. This is typical of Descartes. This is a little piece of genius here, but it's not much of an algorithm. You know, this is not going to be the way to go, guys. And it works here for the parabola, but what about if I draw some crazy curve? You know, I write down any kind of weird equation, I try to find the locus. I can't rely upon it having an axis. I can't rely upon having a symmetric circle that's going to touch it in symmetric ways. This is not going to work for a general curve. So as clever as it is, as important as it is, as a stepping stone, the fact that it's done by Descartes himself deserves to be shown. But no, this is not where we're going. Where we're going is Fermat. Okay, so let us continue on. One more person before we get to Descartes, and that's Roberval. This is very, very clever and very important because this work here will lead to Newton's version of the calculus. Okay, that's why I want to show this. And this is the work of Robomow. Remember when the Greeks found the tangent line to the parabola, we had the directrix and the focus. And remember the locus of the line. The locus of the parabola is the points equidistant from the focus to the directrix. This is literally a slide from our first presentation, guys. So we know that the distance up from the directrix straight up has got to be the same as the distance, from the focus. But we know that, right? We know that that is this, the perpendicular bisector is all the points which are equidistant from the focus to the directrix. Okay, so we just need to find the place on the perpendicular bisector, which is also on this line from the directrix. And so that would be the locus. That's the way we construct the point on the parabola. Okay, but if you remember, I mentioned that this also for free, we also get the tangent line. Not only do we construct the point because it fits the locus, because now the distance from F to the point is the same as the distance from the directrix to the point. That's how the locus is defined in words. And so this is a very, very nice construction. It also for free gives us the tangent line. What I didn't mention at the time was it also gives us that this tangent line bisects that line from the point to the focus and the point to the directrix. A nice little geometric fact, okay, that the Greeks certainly knew. Why is that? Well, right, this is two right triangles. This is the perpendicular bisector, okay? So, this is side angle side, side angle side. This is the perpendicular bisector. This is a common side. This is a right triangle, okay? So these two triangles are congruent and therefore corresponding angles are equal. Roberval sees this and says, wait a minute, this is very interesting. You're telling me that if I think of this point as moving, if I think of this as a moving point, see, which the Greeks would never do. They wouldn't have to. To them, they're constructing a point by point. Their construction is a static one. You give me a point and I'll show you how to construct it. That's as far as they really had to go in their paradigm. Robomow says, if you think of this point as sliding along the parabola, then isn't it true that the distance from F to P is always the same as the distance from D to P? If I think of this as a moving point, okay, let's move to Roberval's point of view now. Okay, if I think of this as a moving point, let's do the construction again. Same construction. You're telling me that the distance from F to P is always the same as the distance from the directrix up to P. And if I think of that as a moving point, then isn't it true that the point P is moving away from F and moving away from D at the same speed? This is a very profound idea, guys. If the distance from F to P is always equal to the distance from P to D, then as P recedes away from F and D or moves down towards F to P, P is moving in the direction of F and in the direction of D at the same speed. Its composite, of course, is staying on the sliding curve, but their components towards those 2 points are equal in speed. So as the point slides up, and if you draw the speed from F, how far it moves away from F, how far away it's moving from D, those two speeds are always the same because the distance is always increasing at the same rate. And therefore, what's the tangent line? The tangent line is nothing more than the composite of those 2 speeds. But since those 2 speeds are equal, the composite is going to be the perpendicular bisector of the two speed vectors. I'm using modern terms of vectors. He would not use the word vector, but the idea is the same. And clearly, we come up with the theorem of well known to the Greeks, that the tangent line is the perpendicular bisector of the line FPD. But he comes about it from a completely different point of view. He's seeing this as a moving point, okay? And this idea of a moving point is taken up by even a greater genius of Newton, and turns this into the calculus, of the physics of motion. So let me show you this very, very pretty animation of this and how far Roberval gets with this idea. This is the actual animation of the Greeks, which we've already seen. Let's go right to Roberval's animation. So what Roberval says is, as you see this point moving, the distance of the two red lines is always the same. Okay, they're growing at exactly the same rate. Okay, they're getting longer and longer at the same rate because these two distances always have to be the same. If you go back the other way, they're shrinking at the same rate, and they start growing back at the same rate. So if you were to look at these as speeds, the speeds are always the same. Sometimes they're approaching the point, and sometimes they're moving away from the point. But the speeds are always the same. So therefore, the composite speed is, of course, the tangent line. Now, the tangent, I'm drawing the long, long tangent line. The composite speed would be, a vector, kind of the vector sum of those. But, Roberval is not there. He's not concerned about the actual composite speed. That's that's a little bit, that's something Galileo would be interested in. Roberval as a geometer is not. He's just saying this characterizes for us, this is how we can characterize the tangent line by being the perpendicular bisector of those speeds, because we're looking at a moving point. Very, very clever idea. Okay, he gets a lot of mileage out of this. Let us take a look at the ellipse. Next one down. Let me remind you about the construction of the ellipse. Many of you will know this. The way to draw an ellipse, guys, is the famous thing is you have a string, you have 2 points on a piece of paper, and this is like a pencil. And as long as you keep the strings taut, it'll draw out an ellipse. That is that this is the fixed length of the string, so that the blue line plus the red line always has the same value. The sum of these two values on any point on the ellipse is the same. And the way you can visualize that is this is a pencil, and you're keeping the string taut, and so therefore the distance of these two lines, although they're changing, always equal the same length, the composite length of the string. Okay, so this is how one way of describing the locus of an ellipse. Very, very nice. Robomow sees the same thing. So wait a minute, you're telling me that as this distance grows longer and longer, this distance red gets shorter and shorter in exactly the same way, because the composite length is always the same. So this thing is always growing. The rate of increase of the blue line is equal to the rate of decrease of the red line, to say it in more calculus terms. Okay, I don't know if Roberval exactly would have said it that way. So again, if we look at the velocity vectors, now the velocity vectors are not like the parabola, where they're always in the same direction. Here, the blue line is moving, this point is moving away from the blue focus, and the point is now moving towards the red focus, as opposed to in the parabola, where they're both moving away together or both moving towards together. Here, one is always moving away and one is moving towards, but the principle is the same. It's really a very, very cool idea. It's exactly the same idea because of the nature of the locus. And so therefore, we have the tangent line. The tangent line, again, is the perpendicular bisector of those two vectors. Very, very nice. Very nice generalization that we don't have to have the vectors, moving towards or away the same points in the configuration, as long as their composite velocity is something that we can recognize. And this, of course, by the way, what you're looking at is a theorem that you prove in analytic geometry. You prove that the lines from the foci to the point, the tangent line does bisect the two extended lines from the point to the foci. This is a theorem in analytic geometry that you prove using the calculus. But Robomow is not finished. Let me show you one more. He goes to the cycloid. Yes, here we go. Okay. This is a curve that we haven't seen before. This curve actually was introduced by Galileo. And it's a very interesting curve. We have this wheel. We've got this point on the wheel. And you just simply turn the wheel on the x-axis, so let the wheel turn, and you watch that point. You watch the point on the rim. It will, set out a curve. This is just a point on a turning wheel on a flat surface. It's a very, very interesting curve. The cycloid. This was studied by everyone. This was studied by Fermat and Descartes and Newton and Huygens and Leibniz. They all got a piece of this. They were interested in how much area was underneath this curve, what the tangent line to the curve was, what the center of gravity, what the centroid of this curve would be, what the arc length would be. Very, very interested in this curve. This was a wonderful example of a new curve that was very exciting to them and had all these wonderful, beautiful properties that they could use their new methods to solve. Robomow uses his same method of motion to find the tangent line. And this is very, very clever. As you look at the point move, okay, what is the composite motion? How is this blue point actually moving as it's falling on the rim? Well, on the one hand, it has to follow the circle. It has to follow the center of the circle as it's moving straight, okay? The circle is simply moving. I'm just noticing here the bottom of the circle so we can track it easily. But basically, the circle is moving in a horizontal direction at a constant speed. At the same time, the circle is moving, right? The circle, I'm sorry, is turning. And so this point is not only being dragged along by the center of the circle, it's also turning up. It's also turning how? A tangent to the circle, right? The motion on any circle at any instant is always tangent to the circle. So this motion, according to Robomow, has two components. Let me move this thing a little bit more to get it like this. This point has two motions as far as Robomow is concerned. It's moving straight this way because it's being dragged along by the big circle, and it's also on a turning circle, so it's moving straight up this way. So it has these two components simultaneously, very similar to the parabola, very similar to the ellipse, but now different kinds of components because of the different motion. So let's go ahead and do that. Let's add our components. And here they are. Okay. Here's one component that's moving straight along, being dragged along by the circle as it rolls on the flat ground. And here's the line always tangent to the circle because this point is on a turning circle, and therefore it has a motion tangent to it. Notice this arrow will always remain tangent to the circle, no matter where the tangent is. Okay. And what Robomow is going to do is he's going to say, well, the tangent line to the cycloid is the composite. And turns out you can prove that the speed of it on the turning circle is the same as the overall speed moving along the ground. That's something you would have to prove to show that these two arrows are of the same length, something we don't have time to prove that Robomow did. And therefore, again, the tangent line would be the perpendicular bisector of this thing. So, and this is something that very much Newton inspires Newton to begin to develop this in an analytic way, and comes with his fluxions and all the rest of finding slope of the tangent line. Okay, with only 5 minutes left, let us, one thing I mention about the cycloid. If you turn the cycloid upside down, it has a very interesting property. If you take these two halves of the cycloid and you force the pendulum to follow its curve, see the flexible pendulum has to be bent by the cycloid arms. It turns out that this curve here is also a cycloid. It has two very interesting properties. One we can see here. No matter where you drop this point, okay? No matter where, can I stop this thing? Oh, no, I guess I can't. Can I stop this thing? No, I guess I can't stop it. Okay, we'll have to work with the moving picture. The idea. Oh, no, I'm sorry, I'm going the wrong way, guys. Here we go. Okay. What this picture is trying to show is you can drop it from the purple height, the blue height, the green height, the orange height, or the red height. No matter where you drop a ball from the cycloid, let it slide down the cycloid only under the influence of gravity, all those balls will reach the bottom at the same time. This was a problem that was proposed by the mathematicians of the day. Is there such a curve that would have this property? That no matter where you dropped it from, it would always hit the bottom at the same time. It has the same period going down. Turns out the cycloid is the solution to this problem. Another just fascinating problem about the cycloid. There's one more that this animation shows us a little bit harder to see. What is the curve that if you drop it anywhere, it would reach the bottom at the fastest time? Would it be a straight line down? Would it be a semicircle down? What's the fastest way to get from anywhere you want to start down to the bottom if it's only moving under the influence of gravity? The answer also is the cycloid. So the mathematicians of the 17th century had great fun with the cycloid, proving all these different features. I must show you a funny story about Robomow. The cycloid is called the Helen of geometry because it led to so many disputes, just like Helen of Troy launched all those thousands of ships. One reason why
you're breaking up quite a bit.
Ah, okay. Well, we're almost at the end. Maybe I may recover. Am I getting any better, Mike?
There's actually a message on your screen, your image saying Mulhall-Peters network bandwidth is low.
Yes.
And it's been there for a couple of minutes.
Okay. Let me turn off my video. Just see. Does that help? Turning off
perhaps.
my video.
I'm hearing you now, and I'm seeing the.
Okay, then I guess we're live again. Okay. Well, I was about to just to tell the story of one more thing about the cycloid, which is interesting. It's called the Helen of geometry, and it's all Roboval's fault. There was all kinds of priority disputes as to who proved what first. All these various things about the cycloid, the centroid, the arc length, area underneath, and et cetera, et cetera. There was tremendous fights as to who was the first one to discover these things. Roboval was at fault because he was the professor of the chair of mathematics at the University of Paris. And the way you kept your chair was every 3 years, you had to have a contest of problems. And whoever solved most of the problems, whoever won the contest, was able to have the chair for the next 3 years. The kicker was the person who made the contest questions was the existing chair, was the incumbent. So Roboval would prove all these things, never publish them, keep them hidden, and he would use them every 3 years to spring it on the people who were trying to get his job. But then after the contest was over, he said, oh, but I proved that 3 years ago. And so, yeah, right, you proved that 3 years ago. And so it's led to all these kinds of fights, and they all kind of centered around the cycloid. Okay, well, we really are out of time. And guys, if you want to kind of finish my thoughts here on developing the algorithm for the derivative, you could go ahead and work through these particular slides. They are kind of in a logical order. I see that symbol again, that message again. You could work through these and you'd be surprised they kind of go in a logical order. But also, if you go back to episode 3, if you want to watch class 3 again, we did all this the first time. Remember, this was like the second time through. We did all these ideas right through the fundamental theorem. We did all these in class 3, if you'd like to kind of see, again, how this all finishes up. So maybe that was the benefit of giving the big overview, that we did get through the overview that I was trying to get here for the whole course. We just never got to the second round of everything we'd like to have gotten to. All right, well, I will stop there. Are there any final questions or comments or anything anybody wants to say about what's gone on here? Now, have I left
There's
you all
nothing in the
speechless?
chat box.
Any final comments?
Hi, Antonia here, Peter. Can you hear me?
Yes, oh, yes. Yes, I can hear you. I don't know if you muted yourself. Any other thoughts?
Can you
before
hear
we-
me, Peter?
Yes, I can. Apparently you can't hear
Okay,
me.
I just wanted to tell you that way back in the beginning, I said the reason I signed up for this was I could not answer the question you posed in your course description about algebra does this, geometry does this, but what does calculus do? And I want to thank you for getting me started on having an answer for that. Thank you.
Well, thank you. Thank you for that comment. All right, guys, we'll sign off here. Again, the teacher's disease of trying to do too much. It's really an occupational hazard. I apologize for not getting to all the ideas that we wanted to get to, but I hope you enjoyed what we did get to. And thank you very much. You've been a great class. My only regret really is that we weren't in person, that we could have interacted even more. All right, guys, I'll end the class.
Thank you, Peter.
Okay,
Thank you, Peter.
Thank
okay.
you, Peter.
you.
Thank you.
Thank you very much.